start. Just want to make a quick word about stuff. So generally I find the class to be very nice, people very polite, everyone's quite pleasure to teach, all that sort of thing. I have heard a couple of negative reports from tutorials, just in terms of very small incidents, just people sometimes getting a bit frustrated when we would take it out of the tutor or being disrespectful to them in some way. So I wasn't there, I don't know exactly what happened. I just want to remind everybody that we're supposed to be respectful to each other, and we're supposed to be respectful to classmates. I should respect my colleagues, I should respect you, etc. Those around you are lovely and delightful, certainly dignity and respect. And we have very clear rules about that in UCD. I kind of hear, voices from the outside telling us, we should be training people a bit better for the workplace. And this is actually the most basic rule of the workplace, is to know how to behave on the topic. So with mind, just trying to keep that in mind, maths can be a little bit frustrating. Sometimes you're asked for computations I don't want to do. But that isn't a reason to cool initiatives. PhD students are going to do something. Anyway, that's all I want to say. I don't know if anyone wanted to raise an issue at this point or make a comment before we move on to the fun stuff. Okay, all right. So I'm going to start a new topic with you. Inverses and determinants. So we're going to switch now our focus entirely to matrices that are square. So the size is n times n. They all have the same number of rows as they have columns. And this is very nice because it means that basically there's more algebra that we can use, or make more powerful techniques and things like that, because these objects have construction. So square matrix, like I said, is just one that has the same number of rows as columns. You can write it as like a whole set of them to be MNR, so M stands for matrix, the little n tells you how big the matrices are, and R is telling us that the coefficients are the real numbers. Okay, so you could also write that as R n times n, is the way to do that. Or we could say n by n matrices. Okay, so what we've seen is that if you take like a 3 by 4 matrix, then we know that we can multiply that by, for example, a 4 by 5 matrix, and the answer is going to be a 3 by 5 matrix. Right? So each one of those matrices lives in a different collection of matrix sizes. But if they're square, then they're always going to be compatible as long as they're the same size. So any two 3 by 3 matrices, I can add them together, I can multiply them together, and the outputs of those products or sums are also going to be 3 by 3 matrices. Right? So you're doing things and you're keeping elements in the set. So the whole set of them has a more strong algebraic structure. Okay, so for example, 3 by 3s, you can say the same thing about 4 by 4s, or n by n, right? So the collection of n times n matrices, the real coefficients, we say is closed with respect to matrix addition and multiplication. That just means that when I perform those operations on a pair of elements in that set, the element stays, the output stays in the set, right? So this addition and multiplication then are described as operations on the set, because the outputs are in the same place as the inputs. Right? So you'll formally hear things like operations and functions next semester. Anyway, so I can talk about the power of a matrix. So we kind of did this already, because I mentioned last week A squared, for example, if A square matrix. So A to the R then is just a matrix A multiplied by itself R times. And in order for this product to be well defined, I would need that these things are square matrices, right? So if the number of rows is different to the number of columns, then A squared would be well defined. Okay, so in this case, I don't have to worry about commutativity, right? It doesn't matter. If I've got this matrix A here, and then I square it, and then I cube it, it doesn't matter whether I multiply this thing on the left by A or on the right by A. I'm going to get the same result, right? So I have commutativity when I'm stuck in just the different powers of A. Okay. So in this collection of n times n matrices, I've got two operations. I've got addition, I've got multiplication, cascade multiplication as well. It's a different thing. I might ask, well, are there special matrices in here that don't change the other matrices when they're involved in an operation? So if I give you a matrix A, and I give you another, I say, is there a matrix B you can find that I can add to A and I just get the old zero matrix? I mean, is there a matrix that I can find that I can add to A and it doesn't change A in any way, right? That would be the matrix that has all zero entries. If I have this guy here, for example, 2, 3, minus 1, 2, and I add to it the all zero matrix, then I just get 2, 3, minus 1, 2 back again. All right, so that means then I can swap that matrix for anything, and I add, say, this O, if O is going to represent the all zero matrix, and that's always going to give me A back again. All right, so this thing is special. That's an additive identity. Right? It doesn't do anything when I stick it in with the operation addition. Multiplication is the other operation. So is there a matrix such that when I multiply any matrix by it, I get the same matrix back again? And so here's an arbitrary matrix A that I picked. Here's a special one I. I'm going to take this matrix and I'm going to multiply A by it, either on the left or on the right. Okay, so if I do this matrix product, we've seen different ways of looking at the matrix product. I can say, well, the first entry here is going to be the scalar product of the first row with the first column, and the second entry here is going to be the scalar product of the first row with the second column, and the entry here is going to be the scalar product of this row with this column, and then the last one will be the scalar product of that one with that column. That's one way of looking at it. We can also look at it by saying that the first column that appears here is found by taking 1 times the first column plus 0 times the second column. And the second column is formed then by taking 0 times the first column plus 1 times the second column. Those are equivalent ways of looking at matrix multiplication. So in that case, you can see that I've got 1 times that column, and then 0 times that column. So this column is going to be the same as the first one. And I've got 0 times this column plus 1 times the second column, so I just get the second column there, and I haven't changed the matrix. Okay, so at least with respect to multiplying on the right, this matrix I acts like an identity, right identity. Okay, if I do it from the other side, I'm taking this product of I times A, multiplying on the left. What I'm doing here, when I'm doing this product, is to make this first row, I'm going to take 1 times the first row plus 0 times the second row. So I just get the first row appearing here. And again, when I take this product to make the second row, I take 0 times the first row plus 1 times the second row, and that generates the second row. So I haven't changed the matrix. Right, so in both cases, I get A as an output when I multiply either on the left or the right by this special matrix I. So that thing I is called a multiplicative inverse. I mean a multiplicative identity. So we just call it the identity. two identities, the additive identity and the multiplicative identity, and the additive identity is called zero, right? The zero matrix. And typically we'll use I to denote this multiplicative identity, so we always reserve that. Okay, so this thing is going to hold, this property is going to be true. It's nothing to do with A. It is only to do with this identity. Okay. Any questions on anything I said about that example? Okay, so in general, if I have a matrix A, so supposing A is equal to A11 to A1n to 1. This, for what I'm about to say, I don't actually need a square matrix, but let's just do that anyway. I'm going to take that, and then I'm going to take, I'm going to multiply it by some vector v. Okay? I'm multiplying by this vector v1, v2, then to vn. Okay? How do I, so this is an n by n, and this is an n by 1. The matrices are compatible, and I'm going to get an n by 1 as the output. N by 1 is the output. So if I multiply this out, I have A11 times V1 plus A12 times V2 up to A1n times Vn. That's the first entry, right? And then the next one is A21 times V1 plus A22 times V2, and we go all the way down, A2n times Vn. That's the second entry, one element. And we go along, do all those. This is the usual definition for matrix vector multiplication. Okay, I'm just going to write this in a slightly different way. I'm going to write this now as a sum of vectors. Sum of n times 1 matrices. That's going to be the first vector in the sum. Okay? Now I'm going to add in another one. And I go all the way across. Okay, everyone agree with that? That second line is equal to the first, this second vector, this thing here, is the same as the first vector. I've just split up all the sums in the first vector. In other words, if I add these vectors together, I get the first one there. Does everyone agree with that? Okay. One more iteration. We're almost there now. So I'm now going to stare at those vectors. What do you notice about the very first vector in the last line? There's something common to every entry. What's the common bit to every entry? This guy here. What do all of these entries have in common? V1, they're all products of V1, so I can take the V1 outside there, right? That vector is a scalar multiple of V1, right? So I can actually write that as V1 times A11, A21, AN1. Okay, I can look at the second one. Everything in there is a product of V2. Every entry is a product of V2. So I can take the V2 outside there. Okay, and then I can go all the way across, and then I've got Vn. I can take that outside. Okay, so this matrix vector product is the same as taking V1 times the first column, right? The first column is A11, A21 down to N1, right? That's the first column. The second thing that I add in is V times the second column, so V2 times the second column. Then I do plus V3 times the third column, etc., until I get to Vn times the last column, okay? So this is another way to view a matrix vector product, okay? So what I'm doing here is I'm taking a kind of a combination of all of the columns of the matrix. I'm squishing them together then to make a separate column. This is the answer, which is this n times 1 vector at the output. You call that a linear combination of the columns. So I'm combining them linearly and I'm allowing scaling and addition, right? But I'm actually seeing this as V1 times that, plus V2 times the next column, etc., down to Vn times the last column. If you see matrix vector multiplication in that way, then it's going to be helpful sometimes if I want to look at some matrix vector products, right? So this is kind of what I was pointing out in the previous example. So if I've got this matrix 1, 2, 3, 4, and I multiply it by this vector 1, 0, the answer to that is 1 times the first column plus 0 times the second column, okay, based on what we just said. So that's just 1 times the first column, and 0 times the second column means just please write down the first column, okay? And if I was to take the same guy, 1, 2, 3, 4, and multiply it by 0, 1, I'm generating another vector, a 2 by 1 vector when I do this matrix vector product. And it is 0 times the first column, so forget about the first column, plus 1 times the second column. So just repeat the second column. So that's just equal to 2, 4. Okay? Now if I put those two vectors 1, 0 and 0, 1 side by side, the first column is going to be this one, 1, 3, and the second column is going to be this one, 2, 4, when I multiply by this matrix 1, 2, 3, 4 on the right. Okay? And I could make the same argument, like a symmetric argument, if I was multiplying the vector, row vector times the matrix. I'd be taking linear combinations of the rows of the matrix. Right. Anyone have any questions about that? Yeah.
I don't know if you explain this, but why is the identity matrix so important?
Well, it's a bit like saying, why is the 1 in the real number so important? So it's more to think about what would happen if you didn't have it. If you have no identity, it's going to, for example, make it difficult to solve equations. That's a practical way of looking at it. But it's just sort of saying that we're collecting together all these algebraic things that could happen. That we have additional multiplication that are well defined. That's kind of step 1. They're well behaved, they're associative, and all this stuff. And now, okay, we have identities with respect to these operations. And I guess maybe none of the things we're going to talk about now would have any meaning if we didn't have an identity. So that's one way to look at it. Any other questions on this bit? Okay, so this computational thing, I find it very hard for people to acknowledge this fact. No one complains when I show it to them, but then when it's useful to use it, it's as if it's a new thing. Okay? So please try and keep in mind the different ways of viewing matrix multiplication. Okay? Any questions? That's it? Right. So here's our general identity matrix, an n times n matrix. So it's just very, very easy to write down. It's got all ones on this thing that we call the main diagonal. The diagonal goes from the top left to the bottom right. It's got zeros elsewhere. If it's really obvious or we don't want to bother, we won't write down the n. We'll just write down I to denote the identity matrix. Okay. This matrix has that property in theorem 55, that when I take any matrix A and I multiply it either on the left or the right by this identity matrix, I get the same matrix back again. Right? So this is an identity with respect to matrix multiplication. And the proof of that is essentially easy to see from what I said on the previous slide. Right? Because if I take A and I multiply it by I on the left, I'm going to be taking, I'm going to be writing, so AI is found by taking A times the first column of the matrix I. So it'll be that thing. Right, that'll be a vector, that'll be a column. The next one would be the column A times the second one. And you go along, and then the last one would be A times the final column of this matrix I. Okay? You said that right at the start when we were introducing matrix multiplication. It's just like n times harder than matrix vector product. You just do it n times. This first matrix vector product says, give me the first row of A, right? Because it's 1 times the first column of A. 1 times the first column and ignore the others. 0 times the other columns added on. When I take 8 and multiply it by 0, 1, 0, and zeros all the way down, it just says write down the second column of A. And go all the way along until I write down the nth column of A. And all I have at the end of that is the columns of A in the same order. Okay? So this doesn't change anything. And then use a symmetric argument that says IA rather, is just IA is found by taking the first row of matrix I and multiplying by A, and then the second row. That's what that's equal to. Okay? This is the first row of A plus 0 times the second row plus 0 times the third row. In other words, just write down the first row of A, just write down the second row of A, just write down the last one. Okay? Okay, so this is, anyway, the property that this matrix has. Okay. Okay, so we have a notion of an identity, additive identity, multiplicative identity, so 0 in the I. So all of algebra, as we know it, basically comes from people trying to solve equations. Try and solve the equations and then it just blows up into a big theory. That's what happens. So if I give you this thing, 2x plus y is equal to 5, for example, okay? And you want to solve for x. You're going to laugh at me and say, well, I know how to do that. I'm just going to say that I'm going to write 2x is equal to 5 minus y, and then I'm going to say that x is equal to 5 minus y over 2. Why are we doing this? Well, maybe I'll write it as 5 minus y times 2 inverse, something like that. Okay. First thing is that equation necessarily something I can solve over the integers anytime? Like the integers are the numbers, the whole numbers, plus, minus, and 0. So could I always solve an equation like that over the integers? So in other words, would x be integer all the time if I did this? No, alright, so this cannot be solved over the integers necessarily. I mean, you could be lucky if you pick y in the right way, but in general, no. Where do I have to go to be able to solve this all the time? What number field contains the integers?
Matrix.
Not exactly, they live in different domains. Something that's a bit bigger than the integers. The rationals would work, right? The real numbers would work, anything. So the rationals would be the smallest thing I could go to always be able to solve this. Why is that? Because I don't have inverse of 2 in the integers, right? There's no number that I can multiply by 2 in the integers that's going to give me 1. So in order for this thing to inverse to make sense, I have to go to a bigger place, right? So we do that, that's what we did. We go and make up the rationals and then we go and solve the equations. Excellent, that's how we discovered the complex numbers, trying to solve equations. Same question, what about matrices? 2 times A plus B is equal to some matrix C, right? So say these are matrices. Let's make it easy on ourselves and just say that these are 2 by 2 matrices. Okay, I could try and solve this thing. So what have I got? I've got 2 times A is equal to C minus B, and then I can say that A is equal to 2 inverse C minus B. Can I always solve that for the matrices? These are matrices over the real numbers. Can I always solve for A in this situation? If I give you matrices A, B, and C, and I give you this equation, are you going to be able to tell me what A is equal to? You are. You are. Okay, so you are. You just have to believe in yourself. Okay? So we know how to subtract matrices from each other. We have no problem subtracting C from B, right? Because they're all 2 by 2 matrices. And I have no problem with multiplying a matrix by a scalar, right? And this 2 inverse, that's a half in the real numbers, right? That's okay. That exists, that's a real number. So I can solve for that, that's all right. But supposing I wanted to jizz up this equation a little bit, and I'm looking at something like A, B plus C is equal to D. Okay, now I want to solve for A. Okay, so I could say that AB is equal to D minus C. Can I solve for A in this equation? What would I like to be able to do in order to be able to solve for A? I'd like to be able to invert B. Okay? If I can invert B, then I can solve for A. Right? So having inverses and identities is going to allow me to solve equations. Right? So if let's just call it the inverse, if it exists, then A is equal to D minus C times B inverse. And if it doesn't exist, maybe I can solve the equation and maybe I can't. It's not clear whether or not this thing is going to have a solution either. Okay? So that's B inverse. Okay. So this is kind of a background. This is motivation for being able to define all the things we're going to do. We're going to be interested in knowing when can we tell if a matrix is invertible. If it is invertible, how do we write down the inverse? How do we compute the inverse? This is what the next couple of weeks are all about. Okay? Okay. So we saw this example last week. We had this 2 by 2 matrix, and basically had this equation. So this 2 by 2 matrix times vector st is equal to xy and we want to put ST in terms of X and Y. So I can treat X and Y basically like constants, and S and T are the variables, because I'm trying to solve for S and T, right? So if I want to solve for S and T, I'm just going to not be disturbed by the X and Y. I'm going to treat them like numbers, and I'm going to go about my business in the usual way, right? If I go about my business the usual way, I take this, which remember this thing here was equal to the vector 2s plus 4t and s minus t. Right? When I do this matrix vector product, that's what I get. That means I'm solving a system of equations. 2s plus 4t is equal to x, and s minus t is equal to y. Right? We said that stuff last week. Okay. So my augmented matrix for the system is this thing. I just go and put it in reduced or echelon form if I can, or if I see how far I can get with it. Don't have any issues arising here with visibility or anything. Don't have to worry about anything to do with X and Y. Okay, so this is now telling me, when I've arrived at this reduced or echelon form, S plus 0 times T is equal to X plus 4Y over 6. And the second thing is telling me that T is equal to X minus 2Y over 6. Okay? So I was able to solve for S and T in terms of X and Y without knowing anything about inverses. Okay? And just apply Gauss-Jordan algorithm like we did, right? Because I can see that this is just about solving equations. Question is there another way of solving this? So can we solve it in the same way that we might maybe solve just an ordinary equation over the reals? So, if I could take this thing on the left-hand side and multiply it by something that brings this to the identity, so an inverse, then I would have an answer that is ST equal to something on the right-hand side. Right? So if this matrix inverse existed, so the product of these two things was equal to the identity matrix, right? If this, when I'm writing it like this, what if this was the answer of the product of just these two things? Then I wouldn't be changing ST, I would have the identity on the left-hand side, and then I would have an expression for ST as this matrix vector product. Okay? So sometimes we can do that. We can always solve this way, and either we'll find 0 solutions, 1 solution, an infinite number of solutions. Sometimes we can solve this way. Supposing we can solve this way, what can you say about S and T? How many solutions are there for that system of equations for fixed X and Y? What would you guess? One. Exactly one. Okay? If this thing exists, then I have a 2 by 2 matrix, and when I multiply by this, I have some vector, and that's determined. Right? So if I can solve this by finding an inverse, I'm going to always be able to solve it, and I'm going to have exactly one answer. Right? So I can solve a smaller number of equations by this approach, but those equations always have a unique solution. Any questions? Okay. So let's have a look at which matrices have multiple inverses. So an inverse, amazing that we managed to get this far without even saying what an inverse is. So an inverse, so A is an inverse of B if A times B is equal to B times A is equal to the identity matrix. That's a definition of what an inverse is. It would be another step to show that inverses are uniquely determined, which we can also do. Okay, so this question is, which square matrices have multiplicative inverses? Is the same as saying, are there values, or are there matrices when I multiply them by A, I get the identity on the left and the right hand side. Okay, so we've got these two. I'm going to look at these two examples, exactly the same ones on this slide. Right? So, first one, we're just going to compute AB. Okay. So I take 2, 1, 5, 3, and I multiply it by 3 minus 1 minus 5, 2. Okay, so 2 by 3 is 6, minus 5 is 1, minus 2 plus 2 is equal to 0, plus 15 minus 15 is equal to 0, and then minus 5 plus 6 is equal to 1. Okay? So B and A look like they're inverse of each other. So far we can see that B is the right inverse of A and A is the left inverse of B. And if I take B times A, so I get 3 minus 1 minus 5, 2, and I multiply that by 2, 1, 5, 3. First entry is 6 minus 5 is 1. You take my word for it there, that you're getting the identity matrix back again. Okay, so A and B are inverses of each other. They're both invertible, and A inverses B inverses vice versa. Okay, the second one. C and D. C, D. 1, 1, 1, 1. D is equal to 1, 1, minus 1, minus 1. If I was to take the dot product of 1, 1 with 1 minus 1, I get 1 minus 1, which is 0. And you can see I'm taking the same dot products each way. Right? So in this entry here, the dot product of the first row and the second column is also going to be 0. The dot product of the second column, second row with the first column is going to be 0, 0. Right? But these are definitely not inverses. Right? This is not equal to I. It's kind of weird, but it's not inverse. And then 1, 1, minus 1, minus 1. Multiply by 1, 1, 1, 1. Take this product. So the first entry there is going to be 2. Dot product of the first row of the second column is also 2. The dot product of the second row with the first column is minus 2 and minus 2. Okay? So also not equal to I. And nice way to remind ourselves that matrix multiplication is not commutative. Okay, so the first two matrices, A and B, they're both invertible. The second matrices, they're actually not invertible. We don't know why they're not invertible yet. The fact that when I multiply them together it gives me 0 means that I have a way of showing that they're not invertible. But I would like to know, well, is it possible that C and D are invertible? It's not like I expect when I write down two random matrices that they're going to be inverses of each other. What's the difference between them if they're not? Okay, so this is the theorem. We're just going to take it as a fact for the moment and then we can prove it. This is the theorem that tells us when 2 by 2 matrices are invertible. Very simple criterion, very nice for 2 by 2 matrices. Okay? So I've got this matrix A, B, C, D. It's invertible if and only if the following thing called its determinant is non-zero. So its determinant in this case is A times D minus B times C. Alright, so it's the product of the elements on the main diagonal minus the product of the other two elements. If that's non-zero, then I can write down its inverse. And its inverse is just equal to 1 over the determinant over the determinant of A times D minus B minus CA. Right? So you just flip the row of A and D, the guys on the main diagonal, and the other lads, C and B, they stay fixed, but we just negate them. Okay? Okay, so if I go back and I look at, one of the previous ones, like this one, 1, 1, minus 1, minus 1. Okay? That matrix, maybe it was invertible, but its inverse wasn't on the previous slide, but we can now check and see if it's invertible. When I check if it's invertible, I'm going to take the product of the elements in the main diagonal, so 1 times minus 1, minus the other two elements, the ones going in the opposite direction, minus 1 times 1, and I have 0, okay? So a very simple way to check and see whether or not a 2 by 2 matrix is invertible, I just do this quick calculation. In that works for any matrix. And you can, with a little bit of thought, see why this is true. Yeah?
Can you explain that one more? Like what
this line here, is it?
no, the A minus 1. Yeah.
This one? So then the inverse is given by this formula. The inverse is this thing, A inverse, times 1 over the determinant, which is equal to that. So you want me to prove it, or is it?
No, like what is the determinant?
So this is the determinant. It's this formula here. Right? So it's just A times D minus B times C. And we just call it the determinant. Okay? There is, if you want to know about determinants, you can find books this thick on determinants. Okay? But this is for 2 by 2 matrix. Okay. Now sometimes people ask me, why is the matrix like this? It doesn't look very symmetric, does it? Okay? The answer is, it just works when you do the product, and if you try to think that you think it looks nicer, it actually won't work. It won't give you the identity. Okay? So this formula just works. Somebody sat down and fiddled around with it and solved a system of equations. They looked at this thing and they went A, B, C, D, and then they did X, Y, Z, W, and then they wrote 1, 0, 0, 1, and they solved for X, Y, Z, W, and that's what they found. Okay? Anyway. Okay, so, for example, step 1 anyway. Always just see, before you really understand what a definition is properly, can I do the things I need to do with it? Can I decide whether or not a matrix is invertible? Okay, so this guy, A is equal to 4, 1, minus 2, 3. Find A inverse if it exists. What do? I write down the formula for the determinant, the determinant in the matrix if it exists. Right, so the determinant of A. The determinant of A, the thing that determines whether or not it's invertible. That's equal to 4 times 3 minus 2 times 1. So that's equal to 12 plus 2 is equal to 14. According to the theorem that we stated without proof, this thing's invertible because its determinant is not equal to 0. Right? So you can do a check and say yes, it's invertible. And now we can use our formula up here. The inverse of that, so A inverse, is equal to 1 over the determinant, which is 14. And then I just take my matrix A and I fiddle with it. So I'm going to swap around the 4 and the 3. 3, 4. I leave the other guy, 1 and minus 2 where they are, but I'm going to negate them. Minus 1, 2. Okay. And if you forget the formula, then keep a simple example so that you can toy with it and write down the right formula. Okay, but you have to know the formula. Okay, so that matrix is invertible, and that's its inverse. And then we can check. Maybe we don't believe that this is true. Okay? A times A inverse. So I would take A, 4, 1, minus 2, 3. And I would multiply it by 3, 2, minus 1, 4. And I'm just going to leave the scalar 1 over 14 outside for a minute. Okay, so 4 by 3 is 12, plus 2 is 14, so that will give me a 1 in that position. 4 times minus 1 is minus 4, plus 4 gives me a 0 in that position. Minus 2 times 3 plus 3 times 2 is going to give me a 0 here, and plus 2 plus 12 is 14, divided by 14 is equal to 1. Okay, so it works. We check our answer, so we don't really have an excuse if we've got the wrong inverse. Any questions on that example? Yeah.
There's a term for the determinant for one. That's it.
We're gonna see. But maybe not now, because it's 3 minutes to. Okay. Okay, here we go. Okay. 2 matrices here, A and B. The second one there is that thing that we call the adjoint of A on the slide with the urban amount. The adjoint of A, or the adjugate of A, is equal to B. Okay, it's just a name, technical term. Okay, if I take A and I multiply it by B, I get A, B, C, D. I'm going to take this B, D minus B minus C, A. Okay? Let's multiply this out. First row, dot product of first row with the first column is A times D plus minus B times C. So AD minus BC. That's the first entry, the 1-1 entry. The 1-2 entry is the dot product of the first row with the second column. So that's A times minus B minus AB plus AB. 2-1 entry is the dot product of the second row of the first column. 2-1 entry, second row of first column. That's going to be CD minus CD. And then the last one is going to be minus CB plus AD. Okay? What's that equal to? AD minus BC, 0, 0, AD minus BC. What's AD minus BC in determinant words? Determinant of A. So this is equal to the determinant of A times the identity matrix. Okay, so it just works. It works. That certainly is a formula that's going to always be in the inverse of A. But we'll see on Fridays that that thing is also weak, and